This video will demonstrate the Computer-Aided Test Station, or CAT, that J.Olka and I conceived, assembled, developed the software for, and tested as our ET450 Capstone project. The project was conceived to provide a target client automation of their assorted test instruments through an extensive software package that operates the instruments under program control. The target client, for example, an audiophile system integrator or a pro audio repair shop, has accumulated a mix of instruments over time as needed, but not with a system goal of automated testing in mind. A computer automated test station eliminates the tedious setup, manual commanding, report generation, and teardown associated with non-automated control. The instruments, system controller, and electronic storage of test data are all connected together with an industry standard IEEE 48 general purpose interface bus, all focused on the device under test. The system software, the main deliverable of the project, when started, automatically detects the presence of the instruments, runs their self-test routines, and assure they pass that, then presents the operator with soft key-driven test choices. The instruments have been detected and are online. We will look at the frequency response routine, the automotive amplifier test, and the gain transfer function. Each test has an associated automatic test report. We'll run a frequency response on a real-world device under test, an Ashley professional equalizer from a sound reinforcement system. Now, to make things interesting, we're going to deliberately move the 4K attenuator just slightly off its center detent to see if the CAT can pick up that dip in frequency response. Selecting the frequency response soft key prompts the user for a name to store the file in, and the input voltage to run the test at. We'll run this at 2 volts RMS. The test begins, and keep the operator apprised. The name of the test is printed on the oscilloscope screen. The function generator is stepping through the frequencies from 20 to 20 kilohertz. The CAT uses a trust but verify logic in that it trusts the function generator to output the intended frequency, but it redundantly measures that frequency with a different instrument, in this case, the oscilloscope. The output voltage of the function generator is, again, trusted to be output at the intended amount, but is tracked with a true RMS voltmeter to ensure that that level is held constant through the duration of the test. The system controller displays each step's frequency and measured voltage. And we could see as we passed through 4 kilohertz, there was a little dip in the frequency response. The test concludes at 20 kilohertz. Selecting the report of this test is conveniently mapped to the shifted soft key of the test, and we call that MQX2150. System controller gives a tabulation of the data, and we do see a little dip at 4 kilohertz. See what that looks like plotted. The plotting routine automatically scales the x-axis and y-axis to the incoming data.
And indeed we see the dip at 4 kilohertz attributed to having that slider off of its center detent. Next up, the automotive amplifier test. This test measures the power output of a 2-channel amplifier as a function of varying DC input voltage. DC input voltages can vary widely in an automotive environment, from as low as 10 volts to as high as 15 volts. Selecting the test prompts the user for a file name, the test frequency, the input voltage, and then the range of VDC input. We'll run this from 10 to 15 volts. The program computes the power output of the amplifier by measuring its output voltage into a known load. So we'll input the known load. The test begins with the oscilloscope set to 2-trace mode and positioning the traces on the screen. Then the signals applied in the amplifier held at the minimum voltage, here 10 volts, for 5 seconds to allow it to stabilize. The DC source then steps up through the test VDC inputs. Again, keeping with the trust but verify logic, the cat trusts that the DC source is outputting the intended voltage. It is redundantly checked with a DMM and stored in the data file. The system controller displays the current VDC input and the power output of the left and right channels as the test commences. The test concludes at the 15 volts maximum, and the DC source has been safely shut off, and the function generator output zeroed. Now running the report, again the shifted key function, will give us a tabulation of the amplifier's performance as a function of EDC in. And we will get a plot of the output. Again, the x-axis and y-axis are automatically scaled to the incoming measured data. And we get a trace to the left and the right channel. We will use the known circuit impairment to demonstrate the gain transfer function using back-to-back Zener diodes as described in the final report to simulate a heavily clipping circuit. Selecting the gain transfer function, soft key, sets up the oscilloscope for a 2-channel measurement, the input on the top trace and the output on the bottom trace. Prompted for a test name, Zener. We'll run this at 1,000 hertz, and we'll push the input up to 5 volts and see how the output responds. Function generator is set to 1,000 hertz, and we'll walk up the amplitude. Test begins at 0.1 volts. It's going to walk up to 5 volts. And at these low voltages of input, we see a linear response in the output, a nice sinusoidal wave on the output as a function of input. System controller is giving us the step input voltage and the corresponding output voltage. So far the Zener diode circuit is behaving linearly. As we get close to the Zener voltage, we can see that the output waveform is starting to clip, similar to an amplifier would being driven into its voltage rails. So we expect to see a very nonlinear gain transfer function when this test completes and is plotted. Running the gain transfer plot of our Zener simulation of a clipping amplifier. Again, the plotting routine is auto-scaling the x-axis to the applied voltage and the y-axis to the output voltage. And there we see a very nonlinear response, clipping at about 2.7 volts as expected for the xenodiode pair. The J.Olka Aliamus ET450 computer-aided test station meets all of its functional specifications and represents 16 weeks of hard work. Can it be improved? Yes, it can. The modular design of the software allows more test types to be added and more instruments to be accommodated. Joe and I learned a great deal about computer-aided testing during the construction and completion of this project. Thank you for watching our video.